Thank you very much. I'm very happy to be here. I'm Mathieu from CEDRAT Technologies, which is a partner of the POSCOM project. So I'm very honored today to introduce you to our company and what we do and what the applications of smart materials can be for opto-electronic applications, including space and others. A few words about CEDRAT Technologies. We are a company specialized in mechatronics, and we mainly work with magnetic and piezoelectric effects. And we design and we build actuators, sensors, and also the electronics that come with it. The company started the activity in 1989, and we are increasing. We are now more than 65 employees. And we are located in Mélan, which is near Grenoble, in the southeast of France. We offer products, but also engineering and sometimes also training. We are active in various applications. Here are the main 5 markets we address. Of course, optronics, but also instrumentation, air and space, manufacturing, and medical technologies. You can find many information on our website, including a corporate video. So here is a view of the main products we offer, which can be made either on commercially off-the-shelf products or also custom products. So these are both magnetic and piezoelectric actuators. And with these actuators, we design more complex products, which we call mechanisms, that can be also either made of magnetic technologies or piezo technologies. And we design and deliver the electronics for that, the driving electronics. So for the magnetic components, usually these are current-controlled electronics, and for piezo, it's voltage-controlled electronics. So now we will go into details of each the products that were in the previous slides. We start with the the parallel prestressed piezo actuator. So this actuator is actually a bunch of piezo stacks, so multi-layer actuators that are available commercially off the shelf. We do not manufacture them, we just buy them. But our added value is what we put around. And what you can see around these ceramics is a spring, and it's a compression spring. And what this spring brings is the capability to apply a preload on the ceramic. And the effect of the preload is to be able to work in dynamic conditions with these actuators without having a breakdown on the ceramics that could occur when you use the ceramic with a sine signal. And due to tensile strength, when you have acceleration, inertia forces, the ceramics are very fragile in tension. So the compression load prevents that. And there's a lot of added value in this spring because it is not just a spring. It is really the design requires a lot of engineering behind that. So this is where we put our core business and added value. An example of an application of this parallel pre-stress actuator is for metal machining. This is a boring bar. This is something you use in a lathe when you turn metal on the inside of a hole. And usually a boring bar is a very long bar because you need to get inside a very narrow area. So it is, of course, vibrating a lot, and it makes a lot of defects on the surface. So we can actively control the vibrations at the end of the tool. And this is what we do with this actuator that compensates the vibrations thanks to sensors and a control loop system. Here you can see an example of a test. On the test, we just put a hammer and we hit the boring bar. The red signal shows how the bar moves without control. And the blue line shows how it is moving when the system is compensating. So we can see that there is a high improvement in the stability, in the damping. Our other main product, and this is a patented product from CEDRAT technology, this is the amplified piezo actuator. The principle is that when this bunch of ceramic stacks expands, it results into a compression movement here on the other ends. So it is a reversed and amplified movement. And the benefit of that is that you can increase the stroke of the piezo actuator. I didn't mention in the previous slide that the typical strokes of a direct piezo is like 10 to 150 microns, which is quite small, but the blocked force is very high. With an amplified piezo actuator, you can go up to 2000 microns. And of course, the trade-off is that the blocked force is a little bit lower, but we are still talking about 2 kilonewton for a standard product, which is very interesting. An example of a product we developed for a custom application is for the extremely large telescope, which is under construction now. This telescope has 5 main mirrors, and we are involved in the M5 mirror, so the last one, and the smallest one, but it's still like 1 or 2 meters wide. And this is quite heavy, even though it is made of silicon carbide. And we made a custom actuator that is very, very strong, and it is used in the active positioning of the mirror to make sure the mirror is perfectly aligned. And this is actually the biggest amplified piezo actuator in the world. And as you can see, it is encapsulated to prevent any humidity to go into the ceramics. The main purpose is to make sure it will have a very high life of service. Let's go now on the actuators, on the magnetic actuators side. This product is a quite original product we made. It's called the Mika Actuator. Mika means moving iron controllable actuator. This means we have an iron, we have a coil, but we have also permanent magnets that polarize the magnetic field. And so this is working with reluctant forces, but with a normal reluctant system, usually you have only one way to move the actuator. Here we have 2 ways, so it's like a voice coil, but quite different, and it has interesting applications. What is interesting is that it is using a flexure bearing. So in this system, there is no really moving parts or no friction parts. So this is very, very reliable, and it has actually been designed for being used in space. Again, we can use these systems for machining control to prevent chattering. So that's the same story as for the boring bar, but here it's for a milling machine. So it's in the like 3 axis, and you can see the spectrum here of a vibration spectrum without the correction and with the dynamic damping. So you can see we completely removed the resonance frequency. Another funny product we make is the Piezo Motor. So the principle of the Piezo Motor is that you use a piezo actuator, but thanks to a friction system, you are able to make some jumps, like a pizzaiolo, you know, when you move the pizza slowly, it follows, but if you do like this, well, it will slip, and you can step by step increase the stroke, the resulting stroke, by adding some small strokes. So this is basically what it is doing.
It's not a piezo motor, it's a pizza motor.
It's a pizza motor, yeah, very good. Bravo. So an example of a piezo motor we customized is this one. This one has been designed for the ITER fusion reactor in Cadarache in France. This is the test bench you see here. But okay, inside a fusion reactor, you sometimes need to move things. But you are in thermal environment, you are in vacuum, you need non-magnetic products, and there's a lot of radiations. So the answer is piezo mechanisms. And of course, you need to control this like 200 meters away because the guys are not inside the reactor, of course. So yeah, this is what we've done. And this is yeah, quite a unique solution for such problems. So here we have a summary of all the products I introduced, which are depicted as a function of the force here and the frequency. So you have the direct piezo with a high force and a low stroke, the amplified piezo with medium force, medium stroke, the piezo motor with high strokes, low forces, and the magnetic products that fill the gap in between. 5 minutes, okay. Now let's come to the mechanisms. This is an XY stage, so it's basically made of 4 push-pull actuators that works in 2 axes, X and Y. And you can move a central load, which is typically a lens, in 2 axes and with strokes from 25 to 400 microns. One interesting application is the microscanning. The principle is that if you form an image on an infrared detector, the infrared detector has very big pixels, usually, or a very low number of pixels because it's quite expensive, especially the cooled infrared sensors. So if you slightly move the lens, you will just shift the image on the pixels. So you can create a combination of four images, but if you combine them with an algorithm, you can recreate a finer image. So this is used for night vision cameras. And you can see here the improvement, like 21 on the left is completely blurred. And 21 on the right, you can see the lines. So this is used in real time by people, and it's 25 pictures per second. So you can imagine how fast this thing is moving in a very precise stroke, like 10 microns. Okay, the second mechanism is the tip tilt mirror. Same principle, but instead of having XY axis, you have angle in 2 directions. So this is also using 4 piezo amplified actuators. And we can reach strokes that are quite low because we are in precision pointing. So typically 1 to 34 milliradian. One application of that is this free space optical communication. Here you have a geostationary satellite and a low Earth orbit satellite. So far, the satellites are communicating with RF communication, which are very broad, so there is no problem of pointing the target. But RF communication is limited in bandwidth, so you want to use laser instead. But you need to be very, very precise in the pointing because the size of the laser on the Earth is like the size of a building. So you cannot make any error on that. So we are talking about microradian precision. Yeah. A few words about another application we mentioned a few times during the summer school. It's the energy harvesting. The amplified piezo actuator has some good properties for that because it has a good energy conversion ratio. So we usually use it for energy harvesting. This is an example of a product that was developed for a feasibility project. We demonstrated that if we put this into an aircraft with the typical vibrations you get in the aircraft, we are able to produce a mean output power of 50 milliwatts. And in this demonstration setup, we were able to create a digital communication between 1 emitter and 1 receiver, all powered by the piezo harvester. And we were basically moving a bar graph with a potentiometer on the left and the bar graph on the right. And the final application I want to mention, it's great because in the previous presentation, we mentioned the structural health monitoring. And this is something that can be done with piezo patches. And we are involved in a project called Cocktail, which aims at developing monitoring systems based on the LAM waves, so like 500 kilohertz frequency typically. And the idea is that we can detect corrosion defects by sending a wave and receiving the wave from other piezo patches. So you can use the piezo patches either as emitters or receivers. And our contribution in that project is to develop the electronics for that. And you can even use this system in the passive mode, which means you can hear corrosion growing, which is quite amazing, but yes, corrosion makes noise. Here you can see a picture that is made from the signals. You can recreate the map of all the damages that you can find on the structure. And here on this project, we target the aeronautics market. So the idea is to make a condition-based maintenance by preventing problems from occurring. So the sooner you get the information, the better it is, and the less time you spend for maintenance. I think I'm right on time. So thank you very much for your attention.